SwayamPrabha. Digital India. Educated India.
So, welcome everybody, welcome back to one more lecture on Introduction to Soft Matter. So, last time we were discussing bonds, right, and the scale of the atom itself. And once we have the atoms, then they actually bond together to form larger objects which we call molecules. And when it comes to atomic bonds, we discussed that there are three primary type of bonds. One would be the covalent bond, and then the ionic bonds and the metallic bonds. For the covalent bond, we discussed that they are highly directional. They also allow for rotational freedom, especially when they are single bonds. Double bonds have have a stronger restriction on the rotation, etc. For ionic bonds, you have an example, for example salt, and they are held together by electrostatic forces. And then finally, we also discussed that we have the metallic bonds, which are considered a variant of the covalent bond, but here the electrons are delocalized in a lattice. So, the part that we did not discuss was the aspect of the secondary bonds. Okay. So, these are the van der Waals bonds. So, in comparison to the primary bonds, they are usually they lack specificity. Okay. So, they usually lack specificity and obviously are going to be less directional and are less directional. So, but what are these bonds? So, what are van der Waals bonds? Now, van der Waals bonds arise from interactions. So, bonds, they arise from interactions between uncharged. So, overall the two entities should not have charges. Uncharged, weakly interacting molecules or atoms. And they are caused by attractive forces or interaction forces between dipoles. Okay. They are caused by interaction between dipoles. Okay. So, that is why we specifically said uncharged, because they actually arise due to dipolar interaction. And if you remember from your perhaps undergraduate or high school level physics, that a dipole is created when you have two charges which are separated from each other and by a certain distance d, and this entity is called a dipole. So, molecules and atoms, they have their own dipoles sometimes. Sometimes the dipoles can be induced by each other, and sometimes the electron clouds themselves are fluctuating in nature. So, there are temporary dipoles in the system. So, those altogether give rise to the van der Waals forces, and here the interaction potential energy, it is usually, so the interaction potential energy usually scales as 1 by r to the power 6. Okay. So, I will just quickly write this, what this is. This is interatomic potential energy between a pair. Okay. And interaction strength, so I will just write it on the side, interaction strength of secondary bonds is usually of the order of 10 to the power minus 20 joules. Okay. Now, just remember that the KBT energy. So, when we are talking about molecules and atoms, the energy scale that we should consider is the KBT energy, where KB, this is a Boltzmann constant, and this is your absolute, this is your temperature in Kelvin scale. Okay. This energy is usually of the order of is of the order of 4 into 10 to the power minus 21 joules. So, we see that the van der Waals forces are just slightly more energetic than the KBT energy. Okay. And even this small increase over the KBT energy is enough to cause van der Waals forces to bring together many different entities together into a structure. Now, since we are discussing the various energies, so I will just maybe write down again secondary bonds are of the order of 10 to the power minus 20 joules. Ionic bonds, on the other hand, have a much larger energy, and they are usually 100 times higher than the secondary bonds, and the covalent bonds also have energies of the order of 100 to the minus 20 joules. Sometimes less, sometimes more. So, but it is of the order of. Okay. So, we are not worried about the exact value here. So, this symbol means approximately or of the order of here. And so, these are the various primary ways in which, and the metallic bonds, by the way, they are more or less of the order of the covalent bonds itself. Right. So, the atoms are going to be held together by some of these forces. So, we should so the atom itself, when we discuss that the Bohr radius itself is of the order of 0.5 Armstrong. So, what is going to be, let us say you put two atoms close by to each other, then they are held together by a bond. So, what is the distance or the equilibrium distance between the two? Okay. So, that is usually called the bond length. So, when you have covalent bonds, and I am going to use a source to get these values. So, let us say the type of bond, and this is the bond length, and the dissociation energy, and this is in kilojoules per mole. So, so for example, if you have the carbon carbon single bond, okay, this bond length is usually around 1.54 Armstrongs, and the dissociation energy is 347 kilojoules per mole. For a carbon carbon double bond, they are actually the distance between the two atoms decreases, and now this is 1.34 Armstrongs, and here the value is 611 kilojoules per mole once again. For a carbon hydrogen bond, you have the bond length being 1.10 Armstrongs, and this value is 411. And for a carbon oxygen bond, the single bond, this is 1.46 Armstrong, and this value is 360. Now, these values I have seen in some sources that differ, the dissociation energy in particular, this slightly differ from these values. So, I will give you the reference from which I have sourced these. So, these are sourced from the book called Polymer Engineering Science and Viscoelasticity by Brinson and Brinson. Now, since we are discussing these distances from the same source, I have put together the values for the bond types. So, the bond types and the distance, this is the approximate distance in these cases. So, for primary or covalent bonds, the distance between the typical distance between the atoms, or the typical separation, is somewhere between 0.1 to 0.2 nanometers. For ionic bonds, the distances can be slightly higher, so 0.2 to 0.3 nanometers. For hydrogen bonds, your distances are larger, or of the order of the ionic bonds sometimes. And finally, the van der Waals bonds, these are the rest of the van der Waals bonds, the distances are usually in this order. So, we can see that for van der Waals forces, they act over slightly larger distances as compared to the covalent bonds, and that is the basic idea that we are trying to give here. So, when atoms come together to form a substance, they have to be held together by certain forces, right. Otherwise, their very basic nature would be to fly away from each other. And then the question is, what is that mechanism that is holding them together, right. And in a given circumstance, it has to be a combination, one of these or a combination of one of these different bonds, which holds all the atoms together into a structure. Now, why are we discussing all this? Remember, in the very beginning, where we discussed the definition of soft matter, we said one of the definitions of soft matter was slightly intuitive, and we said that a soft material is something that is in between a viscous fluid and that of a crystalline solid, right. So, we want to understand how these bonds etc., play a role when it comes to soft materials themselves. So, since we discussed or we contrasted our soft materials with respect to crystalline solids and fluids, maybe we should keep on the discussion a little bit more and see how the contrast really plays out at the atomic level. Okay. So, in an atomic level, when we come to a crystalline solid, the very name crystalline solid tells you probably that the atoms are in some kind of a crystal lattice, and that is the case with metals. Now, they can be in a crystal lattice in many different ways, but let us take a very simple cubic lattice and say we have quickly draw a structure, and let us say we are going to place some atoms at these places, right. So, these atoms are locked in a simple cubic lattice. Now, one can imagine that they are being held together very tightly, and this behavior approximately resembles that of a spring. Okay. So, I am not going to go ahead and complete it, but you get the idea, right. So, let us say the distance between the atoms is A. So, the interatomic distance here we have A. So, atoms are placed in a crystal lattice, and the size of the lattice here is A. So, A is also basically the equilibrium distance between the atoms. So, we will just write that. So, A is equilibrium distance between atoms. Okay. So, when you apply some force and you displace the atoms from this equilibrium distance to maybe a distance of r, there should be a restoring force on the atoms, and that restoring force should be basically some spring constant times r minus a, where r is the displaced distance, right. So, and k is some kind of an effective spring constant here. So, now if we want to figure out how much is the stress, maybe I will just write it there itself. So, to calculate stress, so the stress is force times area. I am just making some very simple calculations. Okay. So, force times area, and here your area is given by a squared, right. So, your stress term, it basically k r minus a by a square. But what is the corresponding strain? So, the strain here, or epsilon, let us say, is r minus a by a, right. So, what is your so this is, let us say this is some kind of tensile stress, and this is your tensile strain. So, what is your Young's modulus in terms of, so the modulus, or let us say E, is the stress versus the strain. So, if you do that here, you would end up with so sigma divided by epsilon, you would end up with k by a, right. So, this tells you that your how your spring constant or this the springs that you have, this imaginary springs that you think are holding the atoms together, if you wanted to assign an effective spring constant, how you can do that, because modulus values are often known from experiments, right. So, if you know the interatomic separation, you can also approximately calculate the spring constant. Now, what is the Young's modulus for steel? Sorry, again, and we are not interested in the exact values. Okay. So, Young's modulus for steel is somewhere of the order of 200 into 200 gigapascals. Whereas, for rubber, this value often comes out to be 0, somewhere around 0.1 to 0.1, 0.01 to 0.1 gigapascals. For Teflon, it can range in some 0.5 gigapascals. Okay. So, the reason I am listing these is because I just want to highlight the difference in magnitude or in the order of magnitude between these quantities, right. So, your steel is your traditional hard material, right. So, this is hard, whereas these two are much softer than steel. So, a little bit loosely speaking, I can say these are much softer materials. So, this also gives you an idea of when we said that soft matter is an intuitive name. One way of looking at it is your traditional soft materials have moduli that are substantially lower than traditional hard materials, and hard materials being something like metals, ceramics, right. So, your rubber and Teflon, obviously they qualify because their moduli are much lower. So, let us carry this on for a little bit longer, this discussion. So, your atoms are actually separated and separated from each other, and basically what is, there is a potential energy associated with an atomic pair. So, let us call this pair potential energy as UR. So, and your A is the equilibrium distance, right, as we discussed that before. So, when you take two atoms and you separate them from each other slightly, displace them from their equilibrium positions, then your U of R, if I want to write it in terms of values at equilibrium, I could say that this is plus some higher order terms. Right. So, the derivative does not exist, does not appear because A is the equilibrium distance. So, U has a minimum at R equal to A. Okay. So, now if we had to compare our original formulation, in which we had said that the force is equal to this spring constant multiplied by r minus a, this gives the restorative force. So, this restorative force has to be related to the pair potential that we are discussing, right. And if you compare the two, so by comparison you can say that k is equal to at r equal to a. So, now what we want to do is see where we are trying to go. We just got the Young's modulus in terms of some spring constant. So, we are going to try and find out what we want to do is we want to find out this Young's modulus in terms of this pair potential energy. So, now we know this relationship, but what is the functional form for u? You cannot calculate this derivative unless you know the functional form. So, let us make an assumption. So, let us say this u r is some kind of some u naught into f by r by a. So, this is I am non-dimensionalizing it. So, this is some dimensionless quantity. Okay. And because you have at r equal to a, your u has a minimum value, some minimum value which is let us say minus u naught. So, this functional form is equal to minus 1. Okay. So, now if you take that particular form, so u naught is representative of some kind of a energy here, right. So, we have the u naught is the quantity where all the energy has gone in. So, if you evaluate now the derivative, so this k now is basically this u naught. If you evaluate k from that particular equation, what you will end up getting is k by a square by d r square f evaluate this entire thing being evaluated at r equal to a. And we already know that the modulus is equal to k by a. So, if you put all of these together, what you end up with is you will find that E is some kind of a constant. So, this derivative, let us say this is some constant and we bundle up all the constants into one, then you can very easily, this is just one step algebra that I am skipping here, you can show that the modulus is some constant u naught by a cube. Okay. So, this is some constant. What this particular form shows us is that the modulus is basically a kind of energy density, right. It is u naught by a cube. So, a cube represents, it is a volumetric term, and u naught, as we had already discussed before, right, it is a pair potential, and we had said that this is that f r by a, this is a dimensionless quantity. So, your u naught is the energy term, right, it has the dimensions of potential energy. So, the modulus is some constant potential energy by some kind of a volume. So, basically it is some kind of a energy density. So, the modulus can be thought of as energy density. But what kind of energy? This is the energy that is getting stored, right, because the atoms are being visualized as being held together by springs. So, the springs are storing energy, and this is the energy density or the storage energy density that is there in the system. Okay. So, today we will stop here, and next class we will begin, we will start off from where we have left today. Okay. So, we will stop here.